Well, hi there. My name is Petter Desne and I work as a lecturer at University of Borås in Sweden. This is a lecture on game design and a lot of other things. First, let's just look at how this game part confirms to the rest of the course. First, you had a C# course to understand some of C#. Then on this course, Windows Forms, ASP.NET, and now game development. And so you got to learn how Visual Studio works graphically, and also about the controls, different things, data grid views in ASP.NET, and you also got to see some other kind of code in ASP.NET, basically XHML. So an XML formatted version of HTML. And I will be speaking about XML also today. And XAML, another version of XML, and pretty close to what you have been doing in Windows Forms, is what we will be using for game development. So today's lecture, first, some things about number crunching. Well, hex notation, colors, 2 to the power of, binary systems, etc. And why is this of interest, also XML and XAML? Well, because this is part of the programmer's toolbox and things that are good to know. And also, if you understand these things, the game development will become easier for you. And game development is part 2 of today's lecture. So first, about number crunching. Well, how much is 2 to the power of 28? And why is my USB drive 16 gigabytes and not 15 gigabytes or 14 gigabytes? Why is it 16 or 32 or 64 or whatever? What color is F167D2 or 010203 or whatever it is, or FFFFFF or FF00FF? What are all those colors? How can you transcribe this into something that you understand? Also, how many characters can be defined in Unicode? What is Unicode? And what does this have to do with, well, anything? Well, if you ever laid in your bed and thinking about these things and can't really get to sleep because all of these things have been worrying you or troubling you somehow, well, then this lecture is for you. The hex notation or hexadecimal notation. Well, first you have the decimal system, which is the one we use, the usual one. It's 10 based, as you know. In the hexadecimal system, the base is 16, which means decima plus hexa in Greek. So, in other words, 0 through 15 are written as just one digit in the hexadecimal system. And since we only have 10 digits in the decimal system, we use the letters A through F to represent 10 to 15, as you can see here in the slide. In hex notation, a color is described using 6 characters, so 2 for red, 2 for green, and 2 for blue, which is why we have the acronym RGB, as in an RGB monitor. So you have F0, 359D or so. So F0 is the amount of red, 35 amount of green, and 9D the amount of blue. And note that 35 is not 35 as in the decimal system. It's actually something else because we're speaking hexadecimal system here. I will return to this. Here's the hexadecimal notation, a list of numbers. So 00 to through to 0f, and then 10 to 1f, etc., until you get to double f. So double f is equal to 255, since it's 16 to the power of 2, and so it's from 0 to 255, or 256 characters in total. Okay, which leads me to colors and why this is of interest to you. Well, why you need to know hex notation. Well, not everyone knows hex notation, but why it is of interest anyway. As I said before, RGB monitors. A computer or a TV monitor, well, it has a number of pixels. Each pixel displays a mix of red, green, and blue. And each color has a number of nuances, or the strength of color, ranging from 0 to 255. This happens to be equal to 2 to the power of 8, I will be speaking of that soon, which is 1 byte. So anyway, as we saw, 255 is also what's referred to as double F in hex notation. Meaning, if we have double F of the color red, we have a lot of red. If we have FF of green, we have a lot of green. If we have nothing, well, we have no color at all, which means black. If we have FF of everything, we have, well, what do we have? Well, we have white. And this is because RGB colors are additive. So the more you have of each color, the more of that color you get. And I will show you some typical colors soon. Once again, the term RGB stands for red, green, blue. So the first two characters describe the amount of red. Characters 3 to 4, how much green you have, and 5 to 6, how much blue you have. So, once again, if you maximize all colors, you will get white, as you see here. Color white, well, in CSS you can write color white, but you could also write hashtag and 6 Fs, or just 3 Fs as a shorthand, meaning that each of the Fs represent R, G, and B in this case. Red corresponds to double F, 0000, or just F00 in shorthand. Green to 00, double F, 00, and blue to 0000, double F. You could also write this with numbers, and as you see there, RGB 25500 is the same thing as writing double F, 0000. You could also get transparency using a fourth variable, the so-called alpha channel, and that is why we refer to this as RGBA. And as you see in the example below, you have RGBA 25500 and then O.35, which means that it's red, but it's not completely red. It's a rather faint color. So it's just a third, basically, of the full color. So this is transparent text. Or it doesn't have to be text, but anyway, the object is transparent. Okay. So how about the binary system? Well, as you see here in my image, you have 16 gig USB memory drive, 32 gigabyte, 64 gigabyte. So it's 16, 32, 64, and not 15, 30, 60 or something like that. And why is that? Oh, sorry. And the final one is also 128-bit, whatever AES is. So there is something about the power of 2 here. So 16, 32, 64, 64, 128. Interesting. And in the binary system, the base is 2, meaning, so instead of meaning it's not 10, it's not 16, it's 2. So all values are either 0 or 1. So to write the number 2, you need another digit. So 2 is written as 10 or 10 in the binary system, as you see in the chart below. Why is this of interest? Well, in a computer, everything is either true or false. You have a number of bits, and 8 bits make up a byte, and then you have kilobyte, megabyte, etc. So for each bit, it's either on or off, or true or false, or dead or alive, whatever you wish, or 1 or 0. And that is the reason why everything is built on the power of 2 on a computer, which is also reflected, as I show you here, on the USB drives. Note also that if you get to roughly 1000 or 1023, 24 here, you get 10 zeros. And this is of interest. It's just by chance, but it's really interesting, and it's really lucky that it looks that way. So, because that makes it easy to convert binary numbers to decimal numbers. Let me show you how this works. First, you need to learn the equivalents up to 1000. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, and then you have 4, 8, 16, 32, 64, 128, 256, 512, and 1024. And you have seen these, I promise you, you have seen these values a number of times. You saw them on the USB drives, 16, 32, 64, 128, and 256. Or perhaps not 256, but 128 anyway. Now, here comes a trick. The tens digit in 2 to the power of something, let's say 2 to the power of 32, take that times 3 and multiply it with 3 and write that many zeros. And before all these zeros, to the left of all these zeros, write the first number, as 2 to the power of 5 is 32. Sorry, not at all. Add whatever is left, like 2 to the power of 2 is 4. Meaning, if you have 2 to the power of 10, you have first a 10 digit, 3 zeros, and then nothing. 2 to the power of 0 is 1. 2 to the power of 20, well, you have 2 times 3 is 6 zeros, and 2 to the power of 0 is 1. 2 to the power of 30, well, you have, once again, you have 3 times 3 in this case, so 9 zeros. 2 to the power of 0 is 1. 2 to the power of 32, you have 3 times 3 zeros, so 9 zeros. 2 to the power of 2 is 4. Meaning 2 to the power of 32 is 4 billion. And this is, for example, the range of an integer in C#, where it's actually plus minus, because you can have negative values. So it's defined as minus 2 to the power of 31, and then between that and 2 to the power of 31. So plus minus 2 billion. 2 to the power of 64 is a lot bigger. It's actually 2 to the power of 32 plus, or 2 to the power of 32 times 2 to the power of 32. So 4 billion times 4 billion is 2 to the power of 64. So 2 to the power of 64, it's not twice as much or so as 2 to the power of 32. Which is also of interest because we are moving now, or we did for a couple of years ago, we moved from computers working with CPUs, working with numbers up to 4 billion, 2 to the power of 32, so 32-bit computers, to 64-bit computers. So these can calculate a lot larger numbers. Actually 4 billion as large numbers as we could previously. Well, once again, this is not really perfect because, as you see here, 2 to the power of 64 is not exactly 16 and all these zeros. It's a bit higher, which has to do with the fact that 2 to the power of 10 is 1024 and not 1000. But it's close enough. You know basically how much all the values are. Here you have some of these values: kilo, mega, giga, tera. And also how you can calculate how much 16 gigabyte USB drive holds. You know that it's 2 to the power of 34 bits, because giga is 9 zeros. So 3 times 3, and then it's 2 to the power of 4, which is 16. So you know it's 2 to the power of 34. You can also calculate the colors of a computer screen this way. They're usually 16.7 millions. And why is that? Well, RGB gives 256 possible intensities of red, of green, and of blue, as you know. And 256 is 2 to the power of 8. So that means that you get 2 to the power of 8 plus 8 plus 8, which is 2 to the power of 24, which is in turn 16 million. Hence, we have 16 million colors on a computer screen. Isn't that nice? How about Unicode? Well, up to the 1990s, the 8-bit ASCII standard was used to define characters in the alphabet, such as A through to Z in capital and lowercase letters, and 09 and some other characters. So what about international characters, or like OOAD or Chinese letters or so? Well, the solution one came up with was to use 2 bytes for each character instead of just 1. So this is Unicode, or the normal version of Unicode. And the downside is that text today takes up twice as much space as it did before. But anyway, people felt that this was the way to go. So that means instead of 1 byte per character, we now have 2 bytes per character. And instead of 2 to the power of 8 possible characters, we now have 2 to the power of 16 possible characters defined. And I leave it to you to figure out how much that is. So a lot of characters are allowed now, and we haven't at all filled the 2 to the power of 16. So there are many spaces left, even though we have, all the normal languages like English and Swedish and German or French and Chinese and Japanese and Korean, etc. And also some more spooky languages like Klingon or Elvish runes and so on. And there are still many characters left. Okay, if you really want to think of this and find out the mathematical values, well, you can use Google. Just type in 2 to the power of 32 and you get exactly how much that is. On the exam, there will be a question on binary notation or similar. So some question related to this. There will also be a question relating to the approximate color of a specific value, such as the one on the slide here. Wow, so there was quite a lot of number crunching. Now let's move on to XML. What is XML? Well, it is a way to organize text, data, etc. in some kind of hierarchy using starting and ending tags, as you already have seen during the ASP.NET lectures. And this sounds, as I said, it sounds like HTML, and in fact, HTML and also HTML5 is basically XML formatted. So a very strict structure of HTML. And I will show you that shortly. One purpose of using XML is to make import and export of data between different software easier. So you have X in docx, XLSX, ASPX, and this X is the file extension that has been added by Microsoft to indicate that these files are saved in some kind of XML format. This means that you can save a Microsoft Office document, for example, as a true XML file. Just choose the file format Word XML document, and you get a lot of information about the styles, and after that you get the actual text. And this can be used. It's not really easy to read, but this can be used by other document softwares like Google Docs or something to import the Word file. In ASP.NET, you've been working with SQL databases, and you can also use XML as a data source. And this is, once again, this is just text, or as you just saw. So this is just a text file. And why should you want to do this? Well, if there is a very limited number of things that you need to use, like a news item on a small website, you wouldn't have to pay for a relational database if you can just use a text file as your data source. Also, it's convenient if you have been given a list for some other person, perhaps created for you automatically every day or so. And this list should be displayed in a grid view or something. Disadvantages of using XML files. Well, it takes quite a while to search through them if they are large, as opposed to a relational database. It's also more difficult, or if it's all possible, to work with several so-called tables, because there are no tables here. Also, note that everything that's being used, well, it says XAML, but it's of course an XML document. It's just a linked CSS file, linked like a CSS file. So the data is not hidden from the user. Here is an XML file example, and this is just a text file. So you have a number of news items here, each called an item, and they have their properties or attributes like an ID, date, heading, text, blah blah blah. And here comes the next item. So you see how they are indented here, meaning how they look. So here starts one, here's the next one, etc. And I can use this text document and browse through it in Visual Studio. I can do that by using a code behind, or I can do it using XML data source in control, in the ASP.NET file. The code itself is not of importance here. I just want to show how it looks on the website. Here I use something called a repeater control, which is basically an unformatted list of data. So as you see here, I have some HTML code, an A element, and then a ruler here, horizontal ruler. So a text here, which is a text from the heading part of my item here, conference registration now opening or whatever. And after that we have the line here. So this is the template for my repeater. And this is the source, the data source for my, sorry, not the data source, the URL for my, or the query string rather, the URL and the query string here for my link to this particular news item using the ID as the query string. So news.aspx, which is the page I'm on, question mark ID equals the ID of the news item. And then I have some code to show this particular news item. Doesn't really matter, this is just to retrieve the query string. Finally, I have once again, well, I have a form view here. It could just be in regular HTML or ASP.NET code. So I have a heading, I have a label, and well, that's about it, I think. Another label here, and a BR tag. And this is fetched from this particular chosen news item. And here are just 2 slides on the entire code for this example. And you can watch this live on my website, the OTech Africa website on news.aspx. And this is what it looks like. So that's how you can use an XML file. The second part of this lecture is about game design. And as you see here on the slide, you see some of the games that the students created on last year this course was given. So you know basically what you can do. And I will speak more about that next time. You will be creating a 2D game with moving graphics. And this might seem somewhat limiting, but on the other hand, there have been countless of such games developed over the past 30 years or even longer. So they are constantly popular, and your game can be popular as well. And to the right, you see Donkey Kong, which I played as a little boy, to the game having sold 48 million copies. So what does a good game need? Well, it needs a good design, the game design itself, a great idea, some good logic code, nice graphics, and of course a great soundtrack and sound effects and so on. So sound and visuals and logic. And more of most of this anyway later on. And here is a tip for you. Don't try to make your game mimic an existing game. Instead, go with your own ideas. This way you can work with the game engine rather than against it. Remember that you don't know how the game engine works. So it's better to not think too hard in advance of what you can do. Computer games have been around for almost as long as computers themselves, or at least as long as they could show graphics, and even before that. Playing computer games became a huge trend very early and increased the pace of the PC evolution. So the speedy evolution of computer processors and other components has, to a large part, taken place because of computer games. That is really interesting, I think. And also note my third point here, that PlayStation, Xbox, and similar, similar boxes, or especially PlayStation, Xbox, they have been very, very well priced in terms of performance. So as far as computer goes, they have been very well priced. Oh, and speaking of which, the game you will develop on this course can be tweaked to run on the web, on smartphones and Xbox, because all of that is possible to do with Visual Studio. So what kind of games do we have? Well, static one-page games like Donkey Kong, or many smartphone games, Angry Birds and so on. Also more complex games such as first-person shooters or FPS. Sports games like soccer, ice hockey, etc. Strategy games like medieval warfare and so on. And word or number games like Sudoku games or Scrabble, etc. And then there are also other kinds of games based on users' movements, rather interesting, like Kinect or Nintendo Wii. The one-page games are easy to start playing, don't require a lot of time, so you can play them on a bus or something. Quite repetitive, so it's usually not a lot that happens in those games. It's also important that you have often many levels, like in Candy Crush, and that the score is updated constantly, and that you have get a huge amount of points at the score. And the graphics are all usually, anyway, rather cheap looking for some reason, low budget. Whereas the complex games, they are usually a bit harder to start playing and require a lot of time, so you can play them for days. And they're very complex because there are so many scenes, characters, rules, and that also means that they get technically more advanced and demanding. And these productions are usually very big, so they have entire graphics departments involved, with hundreds of people actually. In any case, a successful game needs some elements like a good idea or setting, such as an assassin game in the Renaissance Venice, focusing on great graphics and historic details. Okay, so that's the idea. It also needs good gameplay, or spelkänsla. Spelkänsla or gameplay is what we say in Swedish. So good performance and good way to move about in the game. And here is a dedicated gamer keyboard for Counter-Strike. It also needs some eye-catching graphics, nice graphics, and as I said before, also audio. And here you see a screenshot from Assassin's Creed 2, and taking place in Venice. And apart from the excitement of the game itself, you have very nice graphics and a lot of beautiful scenery in the game. In fact, it's so beautiful, the scenery here. So, well, you can read it for yourself. My grandparents love Venice, so I let them play Assassin's Creed 2. They took it in turns to gesture around with a gondola for over an hour. I think that is really sweet, and it's also interesting so you can think about what a game really is and who should be playing it, and does play a game really make sense, or could it be something else? The Swedish game industry is large. It has a yearly income of several billion kronor. Companies like Digital Illusions or DICE with the Battlefield series, and King with the Candy Crush series, and many smaller developers. One of those is Minecraft, which was bought by Microsoft for $2 billion a few years ago, with a very low tech look, which is interesting in itself. How about graphics and OO in games or movies? Well, that's an interesting aspect, I think. When creating graphics for movies or 3D games, you have many objects, and these are created as mathematical models consisting of many small polygons, actually triangles usually, representing the surfaces. And each of these triangles can have a fill color or fill image, just like the objects in the games you're about to develop, or any kind of application you're working on in Visual Studio. And as long as persons are working on this production, the graphics designer sees only the shape as these polygons, and this is called wireframing. It's what you see below with the Yoda image. And during final production, these are calculated using all these images, fill colors that have been decided, and also very important is lighting and shading, which is calculated as well. This process is what is referred to rendering, and it takes many hours for each scene. So this is the resulting image after rendering. And as I said, it takes a long time even for today's computers to do this. And on the next slides, well, there are a few shots from the movie Battleship. There's also an interview about these with a link, as you saw. This screenshot is from the end titles of that movie. So if you watch that movie, look at the end titles. It's really interesting to see all these ships move about. And as you see, you have a wireframe for the bomb, and the bombs are attacking the ship down here. You have the alien vessel over here, and you have the US Navy ship here, and also just a plane here for representing the ocean. So that is all, and then it's just to, like a small child, you can use your computer to move these around, all these different vessels. So what will this look like when rendered? Well, it looks like this. Or, well, like this, no. That's the instances of the bomb class. So it's a class called a bomb or so, and these are the instances. So it looks like no. Well, so what does it look like? Well, it looks like this. There we go. So from this to this. Very impressive, I must say. Once again, it will take many hours for the computers to render all this, including all the reflections from the water and many things like that. Everything here is, of course, computer generated. And here you see all the instances of the bomb class again. Very impressive. So you have the bomb here, and the bomb is just created once, but it's used many times over in the attack towards the battleship here. So the bomb is a body in the 3D animation software, and you will do more or less the same thing in your game. However, in a game there is no time for that kind of rendering, so there must obviously be some shortcuts made to make decent graphics anyway in real time. And the trick here is to have more detailed graphics for objects that are near, like here, like the arm perhaps of this person, and fewer polygons for objects that are far away, like this tank. And then you see a very photorealistic image of a face here, which is not that strange because it is a photo just pasted on this model. And if you have a photorealistic game such as a war game, and there are many of these kinds of games, and if you create a random soldier, this soldier will have a randomized face, so there are many faces available for the game to choose from, and that creates an illusion of unique soldiers in the game. In the same way, each soldier gets a randomized height, perhaps weapon, perhaps strength, hit points, and so on, things like this. And you can do the same thing in your game, so you can randomize everything if you wish. So if you have a very realistic game, you need an arsenal of graphic elements that can be combined so that the user believes that these are different things, where in truth they aren't at all. And in a recent interview for the Polish game called The Witcher, the leader of the game studio tells that they have over 2,000 faces made, and all these faces can be prolonged or shortened or completed with scars or bared and so on, and then added to the characters of the game. And all of this can be randomized, I said, especially for less important characters, that it doesn't really matter what they look like. And the same is of course true for buildings, terrain, etc. You have a number of images combined to create many new environments, or at least that's what the player believes. So here's the question: how many objects do you see here in The Witcher? Well, you have the lead character, I assume, here, and then 2 other figures over here, and then say 100 people in the market. So all of these are different person objects. You have some birds up here, 2 other objects, or instances of the class called bird, perhaps, and so on and so on. All these houses and everything here are just instances of either a body class or a person class or a horse class, a bird class, and house class, etc. So that's interesting, I think, to think of in OO terms. Okay, so the next time you will look at how to create your own 2D game. This is 3D obviously, but how to create your own 2D game. Not very difficult, but more difficult than what you've done before. And I believe that is all for today. And so next time, let's look at the game engine and the logic code of a game. I will also speak more about XAML, and that means that you will understand more why I have been speaking about XML on this lecture. So, thanks for watching this.